All right, so welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Youngseo Kim from Cornell University. Youngseo is not a new face to many of you. She's a PhD candidate in civil and environmental engineering at Cornell. Actually, first of all, with a minor in operations research, but second, also she just defended that she's wrapping up her thesis. Something about Youngseo, she earned both bachelor's and master's of science in civil and environmental engineering from Seoul National University. And she will soon start as an assistant professor in civil and environmental engineering at UCLA, starting in July 2025. So this is, I've been following her trajectory. It's very exciting to see her now move into the next job. Youngseo focuses on transportation engineering. The methods she uses are focused on discrete and convex optimization, discrete choice modeling, and deep and reinforcement learning. And the lab she's creating will work and continue this work on solving design and operational problems in complex interconnected systems, including both transportation and logistics, with a particular emphasis on human behavior. Notably, she was also a visiting student, both in my group remotely and in Kati Wu's group here at MIT in Leeds. I've been following her for many years now, for a couple of years now, and I think what she's doing is amazing. So I think it's great to have her give an autonomy talk. And specifically today, she's going to talk about strategic decision-making in smart mobility networks, integrating supply and demand. So if you have questions during the talk, feel free to put them in the chat. Without further ado, Youngseo, the stage is yours. Please go ahead.
Thank you so much. Thank you for the kind introduction, and thank you for inviting me over. Giving a presentation in the Autonomy Talk has been in the bucket list, so I'm so excited today. So since I need to cover various topics today, let me just get started. So I will start with explaining how I envision smart mobility system, and I'm going to persuade you why is it important to integrate supply and demand in the strategic decision making. So with the advanced technology, there are innovative smart mobility services like mobility as a service. You can simply think it as a platform that integrates many different types of transportation options, and it provides multimodal routes for travelers and provide ultimate user convenience. There is a concept called mobility on demand. So instead of having fixed line and schedule, we can send vehicles to customer on demand. So there is other popular concept like connected and autonomous vehicle and aviation mobility. And to put them all together, we loosely define it as a smart mobility system. And since there are multiple agents having different objectives in our system, they may see different opportunities. So for example, governments may try to find a more sustainable and equitable solution for the new era of this mobility service. And mobility service provider may want to find new momentum for growth. And travelers find more affordable, faster, and more convenient transportation options. So far, decision-making in smart mobility system has been focused on self-interested agents and by usually taking the particular perspective of the agent. What I envision is the integrated decision-making to reconcile the conflicting interests of multiple stakeholders. Ideally, what I want to achieve is the mobility system that is good for all. All means that consider all different types of stakeholders, and good means to help them to achieve their own goal. I know it sounds too ideal, but after this talk, you will see that how all of my research is going toward the same directions, moving toward the smart mobility system that is good for all. But apparently, this problem is really challenging, and there are multiple sources of complexity. One source of complexity is coming from modeling the group behavior. This is actually more complicated than modeling individual behavior because of the competition for limited resources. So for example, companies compete with each other to gain more market share. And travelers also compete with each other in the capacitated road network. Another complexity is coming from the interaction among multiple stakeholders. So for example, the travelers try to maximize utility. Mobility service provider try to maximize their profitability. And government cares about social impacts. And there are two leading decision maker, which is government and mobility service provider. And this is because mobility service provider provides service availability and the price for the travelers. And also government design and construct the infrastructure to travelers. And government and the mobility service provider also interact with each other through taxation and regulation. But in this system, who has the final say? So you know the answer, right? This is a rhetorical question. The final decision maker is really the travelers because their choice on transportation modes, which modes to take, it affects market share, which again affect companies' profitability. And travelers' travel patterns affects social externality that governments care about. So I would like to summarize the challenges into three aspects. One, human behavior is complicated, and we don't yet know the exact impact, like what changes the innovative smart mobility system will bring to our society. And the second is the strategic interaction among multiple stakeholders. And the third aspect is the inherent complexity within the network system. So you can simply think about the real world network and all the passenger and vehicle flows in the complicated network. And more importantly, those components are interconnected to each other, which add extra layer of complexity to the system. So in the ideal decision-making scenario, we need to consider the complicated human behavior on the passenger side, like the traveler side, and we need to consider the network complexity on the supply side. But two different modeling paradigms, each for supply and demand, have been developed separately. So on the demand side, to model the traveler's behavior, discrete choice model has been used as a popular tool. But it is typically analyzed at an aggregated level, disregarding network topology. On the supply side, many people use mathematical programming, which is a really powerful tool. But because of the inherent network complexity, they usually ignore the endogenous travel demand. And combining those two modeling paradigm is not really trivial. And one most intuitive way of approaching it is to take the supply side decision maker as a leader and think demand side decision maker as a follower. And then we keep iterate those two problems until reach to a convergence, but the theoretical convergence might not be guaranteed. So this bi-level structure is held to solve both analytically and numerically. So what I aim to do is to bridge the supply and demand side by integrating choice modeling into the network optimization problem. And my unified framework has three characteristics. One, it can consider complicated human behavior. Second, it considers complexity within the network. And third, it considers multiple stakeholders within the single model. As tools to model the traveler's behavior, I use discrete choice modeling. And to model the supply side decision-making, I use optimization and deep and reinforcement learning. So today's talk will be divided into three pieces.
Youngseo, there is a question from Mohammed.
Yeah, sorry for the interruption. Just to make sure that I'm understanding the flow. Yeah, what's the difference between this bi-level structure that you just mentioned and like what people call Stackelberg gain
Oh, that's a great question. My understanding is that the bi-level structure is more general term. So when people talk about bi-level, usually it has like upper level and the lower level decision making, and assuming the upper level is the leader and the like lower level as a follower, and then keep iterate through it. And then stackable game is the part of this like generalized term.
All right, but what I understand from Stackelberg is like almost exactly as you just described. Like there's a
Right.
there's a follower, and then they keep iterating, like interacting together.
Right, exactly. That's why I'm saying it's a generalized verb, like generalized term, bi-level
Okay.
because
Okay.
it does not need to be like transportation problem. It can be anything
Okay.
when
Okay.
bi-level structure.
Okay. 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 Thank
I
you.
think your understanding is correct. Thank you for the question. So move on to the organization of the talk. Today's talk will be divided into three pieces. I'll start from real-time operation and then move on to the tactical policy development. And then I'll move on to the topic of the long-term planning. And I will present total of 3 different research projects as a separate research because they have their own motivation and application area. But after this talk, you will see that how all of my research is going toward the same direction. So let me first focus on the first area, which is operational efficiency of the mobility on demand. So in this topic, I'll take the perspective of mobility service provider, and assuming that they know the preference of the travelers and they make some behavior-aware decision. So let me start by motivation, by explaining the motivation. The motivation is the emerging mobility on-demand pooling services. So there is different types of service like ride pooling. So you can simply think it as an Uber pool where passenger can share rides with others if they share the similar destination. There is a service like microtransit service, and public transit agency usually operate shuttle van or minibus to help passengers to access to nearby transit station. And compared to the ride-hailing service, those kind of on-demand pooling service can reduce vehicle miles travel by while serving the same amount of passenger. And it can complement the fixed line transit to help them to access to nearby transit station. I was a part of the large project operating pilot service in the real city in the United States. And this project has been funded by NSF and DOE and by collaborating with multiple institute and private company and the public transit agency. We first operate microtransit service in Kansas City, Washington, with the collaboration with King County Metro. And also in different pilot operation, we collaborated with Caltech, Chattanooga Regional Transit Authority, and we operate paratransit service in the Chattanooga area, Tennessee. And our team developed the efficient operation algorithm, and our algorithm has been embedded into their system. And through this experience, I learned that how is it important to develop the efficient operating algorithm for mobility on demand. And this is really the key for the successful adoption. And to give you more background, I'll explain how it works in the backend vehicle scheduling engine. So in our system, the request comes in real time, and we need to solve it in a batch processing technique. What I mean by that is that we are solving the optimization problem every few seconds. So we have a centralized online planner, which is our core technical piece. And then afterward, we receive feedback from the viewer. And at a core, the centralized online planner decide what is the best passenger and vehicle matching, and also decide what is the best vehicle route. So the input of our model is all the passenger and vehicle location information. And the output is for each vehicle, which request to serve in what order through which route. And afterward, we are receiving the real world feedback by observing what is really happening in the real world. So we observe what is the actual user choice, and we track the vehicle movement. And then we move on to the next batch. We are solving optimization problem again, observing real world feedback again, and then we keep iterate through this process until we reach to the end of the day. So in this research thread, developing vehicle scheduling algorithm for operational efficiency, I've been using techniques in operational research and computer science. So in one project, I applied control technique to solve day-ahead scheduling problem for paratransit operation. And in another problem, I applied reinforcement learning technique to overcome the myopic nature of the real-time decision-making. And in the last project, I applied deep learning technique, especially imitation learning, to solve the optimization faster by learning through the distribution. And today, I'm going to focus on one of my research projects, which I apply reinforcement learning technique. So let me deep dive into the problem definition. So if you think about developing algorithm for ride pooling service, this is actually more complicated than algorithm for ride hailing system. The main difference is from the innate service characteristic. So if you think about using ride hailing system, then the estimated time arrival usually provided as a single value. But if you use ride pooling service, then the estimated time arrival usually provided as a range because of the uncertainty to share rides with others. To make this problem extra clear, I'll explain the time axis once the passengers comes into our system. So when the request comes in, we can calculate what is the earliest possible estimated time arrival for the first passenger. And then by adding the maximum detour, we can provide estimated time arrival as a range. And then when the second passengers comes into our system, a vehicle can make detour to pick up the additional passenger. And the first passenger's estimated time arrival will be updated. But what we need to guarantee here is that this updated ETA, estimated time arrival, should be within the promised range. So here, deciding what is the optimal maximum detour, it becomes important. And you can simply think it as a slack in time or flexibility to make detours in the future. But deciding is not really trivial because of the following trade-off. If you think about the case with the small slack time, then on the passenger's perspective, acceptance probability will goes up because they know that they will arrive soon enough. But if you think about the vehicle's perspective, then the flexibility to make detour in the future goes down because their arrival time is too tight. And if you think about the case with the large slack time, it will be the other way around. So we have new decision variable, which is the slack time, and we also need to decide what is the best passenger and vehicle matching pair. And although I kind of omit all the explanation about the routes, we also decide what is the best route for the vehicle at the same time. So at a core, we solve discrete optimization problem. And our goal is to maximize profit for a day, and we need to balance between immediate gain and the future gain. So to estimate the immediate gain, we incorporate the choice modeling to estimate the choice probability on the passenger side. And we also incorporate reinforcement learning technique to estimate what is the state value of each vehicle. So the main contribution of this paper is that we are the first mobility on-demand matching algorithm to develop the optimal slack time. So just like previous approach, many of the researchers incorporate reinforcement learning technique to overcome the myopic nature of real-time decision making, especially for the passenger and vehicle matching problem. What we add is the incorporation of choice modeling into the system, and it gives us additional feature to decide what is the optimal slack time. And we conducted numerical experiments, and we used the New York City taxi data, and we compare our algorithm with the previous approach. And our reinforcement learning approach with the dynamic slack time outperforms all the baseline. And this integration is especially meaningful because we connect system level optimization problem into individual level analysis. What I mean by that is that we have system level decision variables like maximum detour and the price. And we can measure the impact of those service quality on the choice probability on the individual level. And then you can take this entire framework as a simulation and then use it as a design tool. So if you don't have any question, I'll move on to the second area, which is company travelers equilibrium and policy design tool. So let's switch gear to the second topic. And in this research area, I'll take the perspective of the mobility service provider. And we will model the interaction between travelers and the mobility service provider. And then afterward, I'll discuss how the government can use our model as a policy design tool. So the motivation of this research is the emerging transportation network companies like Lyft, Uber, and Didi. And there is some ongoing discussion of what is the exact impact of this transportation network company on our society. Some advocators says it can complement public transit and it can reduce dependency on the private vehicle by suggesting some alternative options. But the critic says these ride-hailing services competing with public transit, and it actually increased road congestion. So to maximize the benefit and to minimize the negative externality, the government needs to develop the policy design tool. And this policy design tool will provide the basis for new regulations and taxation. However, the traditional microeconomic approach is not enough because of the following complexity. So this is the complex system that I want to model. So since the original problem is too complicated, let me focus on the special case with a single company. So you can simply think about a city where Uber monopolizing the entire ride-hailing market. But the single company can operate multiple services, just like Uber operating UberX and UberXL. And company can decide price to maximize their profits. And they can also decide what is their route, considering the congested travel time. And this travel time in congested roads is related to operation costs, which related to their profit. And among those services provided, travelers can choose one of the options to maximize their utility. And they make the decision considering the travel time in the congested road. And travelers' decision affects market share, which again affects profit of the companies. And then company need to revisit their decision on pricing and routing to maximize their profit. So we iterate through this decision of the leading decision maker as a leading decision maker, which is the company, and then following decision maker, which is travelers, and then we keep iterate this iteration until we reach to a point where we define it as a company travelers equilibrium. And at this stage, company cannot increase their profit by changing their pricing and routing strategies. So our goal is to characterize the equilibrium in this complicated multi-agent game. And we model these as a tractable convex programming. And our model connects the game of the traveler sharing resources and profit maximizing company. So our model characterized the best strategy for the profit maximizing company considering the traveler's reactions. So to explain how we were able to model this seemingly intractable complicated situation with the tractable model, I would like to explain what is entropy maximization principle. So let's take an example with the multinomial logic model, which is the simplest discrete choice model. So if you're not familiar with what is a multinomial logic model, you can simply think it as a black box, a function, which takes utilities as an input. And utility can be calculated by known quantities like travel time, travel cost, like the number of transfer, and so on. And then as an output, we know what is the choice probability for choosing each mode M. So we basically know the probability of choosing of transportation modes. So if you think about embedding this multinomial logic model into complicated optimization problem, this brings intractability because this function is nonlinear and non-convex. But luckily, what we can do is to find the equivalent form of optimization problem, which is known as entropy maximization problem. And after it has the decision variable, which is the choice probability. And after solving this problem, we'll get the optimal solution. And this optimal solution is actually exactly the same as the one we can obtain by calculating the probability using the multinomial logic model. And this equivalence can be easily shown by solving the first order condition of the right-hand side optimization problem. So it allows us to substitute the multinomial logic model with the optimization model. To give you more insight about the equivalence of two problems, a multinomial logic model is based on random utility theory, assuming travelers maximize their utility. And there is also has the concept, like the term, maximizing the total utility in the optimization problem. Also, in multinomial logic model, we assume error term follows Gumbel distribution. And we have the corresponding uncertainty term in the optimization problem. And as a constraint, we are ensuring the probability all sum up to 1 to ensure the feasible probability. And this uncertainty term can be characterized through well-known entropy function. That's why we call this entire model as a entropy maximization problem. And entropy function is known to be convex. And it has many econometric interpretation, like the value of choice variety and the information cost. So the entire problem proven to be a convex program. And why do we care about the convex program? Because of the many nice mathematical properties. Some of the properties are the existence of the solution and all the local optimal solution that we can find proven to be a global optimal solution. And all of those nice mathematical property lets algorithmic development like gradient descent and interior point methods. And it gives us tractability to the problem. So going back to our problem, this equivalence transformation allows us the better integration of discrete choice modeling into complicated optimization problem. So this transformation gives us a lot of flexibility especially when we deal with some network environment like transportation problem. And there should be a lot of application, but I will explain one of the application area using our research. but you can also apply the same technique to many different types of application. So let's come back to our original problem, considering the profit maximization, considering the traveler's reaction. So we have decision variable, which is price, that companies decide. And although we have our other decision variable related to routing decision, for example, but I just bring some generic like formulation. And our objective function is to maximize profit, which is revenue minus operation costs. And revenue is the multiplication of the vector of demand, choice probability, and the price. And as a constraint, we are expressing the choice probability as a function of price. So what makes this problem complicated is that price is something that company decide, but it also impacts on traveler's decision. So it's like kind of coupled problem. Also, we usually use multinomial logic model to express the choice probability as a function of price, but it will bring the non-linear constraint. So the solution idea is simple. We are obtaining the inverse function of multinomial logic, and then we are expressing the price as a function of choice probability. And then we plug it into our original objective function. So we are converting the domain from price to choice probability. And as you can expect, the objective function turns out to be a convex. And our theorem shows that the equivalent transformation formulation, it turns out to be a convex program. And after solving this new equivalent formulation, we can obtain what is the optimal price that we wanted to obtain by using the 101 correspondence of the multinomial logic model. So the main contribution of this paper is that we are the first to leverage the entropy principle in the transportation network analysis. So this is our actual objective function. I'll just explain the components. Let's ignore all the notation. But this term can be interpreted as total utility. And we can also recover the entropy function. So you can think these two are the byproducts of embedding discrete choice model into more complicated optimization problem. And we also have the term explaining the operation cost. We are trying to minimize the operation cost, which is associated with all the vehicle movement related to rebalancing costs and the passenger flow. And lastly, we have the term which can be interpreted as the profit extracting behavior of the monopolistic company. So the nice thing about this equivalent formulation is that we were able to write down the closed form objective function, which are totally interpretable. So now we have a convex model to characterize the equilibrium, and which takes all the city-related characteristic as an input, like network, travel demand, traveler's preference, and the fuel cost. And then we can also quantify all the metric as an output. So government can use it to design the new regulation for the city. So to explain it in more detail, I bring the case study. Let's ignore the values for now, but I'll explain how we can use our model in the real world. So we can do some scenario-based analysis, like compared to the baseline solution. What if we add transit line? What if we impose fuel taxes or congestion toll? What if we regulate the total fleet size? For all of this scenario, what we can do is to quantify the following metric, like the changes in consumer surplus, market share, total profit of the company, and congestion level in the entire city, and the total travel time. And those metrics are related to important keywords like energy consumption, congestion level, and emission. So as an extension of this research, since we've been focused on special case, we are in a process of extending it to multiple companies' situation. to get some empirical equilibrium of this competition situation. And mobility service provider can use it as a tool to decide whether to enter into the market or not. And government can also design regulation to mitigate the competition of the companies. So our integrated framework can support decision for a business model and the public policy. So I will move on to the third topic, if you don't have any question. Yeah, let's switch gear to the third topic, which is trouble demand modeling for infrastructure planning. So in this topic, I will focus on the government's perspective. And then assuming that the infrastructure is given to the travelers, we want to model the travelers, like we want to characterize the travelers' demand patterns. And to explain what is the travel demand modeling, this is a process of fully understanding the travel demand pattern in the entire city network. So we need to solve the sequence of the following questions, like where are people coming from? Where are people heading to? What are the transportation mode they choose? And which route they take? And using the transportation terminology, this is a process of modeling origin, destination, and mode route choice for the group behavior. But modeling this is not really trivial because, for example, if I make a decision for the route choice, if I decide to use specific routes, then I contribute to the congestion. And then the congestion will impact on my route decision and also my mode and destination choice. So modeling this travel demand pattern in the entire city network is not really trivial, but it's really important because of many economic values. And one important application is when evaluating the benefit-cost ratio for large-scale infrastructure projects. So if you think about building new roads or transit line, we need to predict what is the future travel demand to estimate what is the benefit of this construction. And the associated costs are massive. For example, US government spent $55 billion on highway construction, and they spent $27 billion on mass transit construction. And inaccurate estimate cause a lot of social costs, like underestimation cause traveler dissatisfaction, and overestimation cause wasted government spending. So to explain what is the popular method that often used in the practice, people usually use the four-step sequential modeling process. So as an input, we take the city network, transportation network, and we take all the available transportation services. And we also use some information like population or rent use. And then we need to go through the sequential modeling process, modeling origin, destination, and mode and route choice. And using the terminology in the sequential modeling, it is called as trip generation, trip distribution, model split, and traffic assignment. And afterward, we get the information of the flow. And this is the link traffic count. You can just think this link traffic count as the number of cars on each road segment. And among all four steps, traffic assignment is the most computationally demanding process. So what people usually do is to use this kind of commercial software like ME4, and this is the map of South Korea visualizing the solution after the traffic assignment. And width of the link is proportional to the traffic count, like the number of cars on the roads. And after getting this simulation outcome, we need to compare it with observation from the real world. And we need to repeat this process to minimize the error between simulation output and the observations. So just like in many other simulations, we need to go through this iterative adjustment process for the parameter. What I proposed is the combined model so that we can eliminate the process of this iterative adjustment of the parameter. So our model provides the more robust parameter estimate by automating this iterative calibration process. And using this combined model with the calibrated parameter, what we can do is to predict future travel patterns after construction, after adopting innovative mobility services, or after changes in demographics over time. So the key contribution is that our paper is present the first model to incorporate parameter calibration in the combined convex program. So compared to the previous approach, taking sequential modeling process, our approach combine all steps, and it can connect the game of the travelers in congested roads and the built infrastructure. And our integrative model connects urban planning with the analysis of the mobility pattern. So going back to our problem, if you really think about where the challenges is coming from, this is really coming from the incomplete observation. So if you take a look at this visualization, and each gray line represents individual travel trajectory. Since our city network is too large, and since there are too many travelers, we cannot observe all of the travel pattern. Instead, what we can get is the incomplete observation, like sparse and point-based travel counts, like data from roof detector or camera. Or we can sometimes observe the full trajectory, but for a subset of travelers, like cell phone GPS data or smart car data. And what I propose is to complement this incomplete observation with the theory-driven model. And I'll use the parametric and aggregated model, which is called as hierarchical logic model. This model called hierarchical model because we are modeling the layer of choice of destination, modes, and routes. And we use corresponding logic models for each layer of choice, specifically multinomial logic model for destination choice, nested logic model for mode choice, and path side logic model for the route choice. So we incorporate the flexible choice model with the rich behavior detail. So what we present is the two-stage model, first estimate and second predict. So in the first stage model, we estimate the parameter, and at the same time, we reconstruct the current travel pattern. And using the parameter that we estimate in the first stage, in the second stage, we predict the future travel pattern. So this is the entire formulation. I'll walk you through the formulation for the first stage, and I'll focus on the first stage model because once we formulate the first stage, modeling the second stage is mathematically trivial. So the objective function is the linear summation of entropy function and Beckman equation. And entropy function, we already covered what is the meaning of entropy function. This is equivalent to choice model, and it measured the uncertainty of choice. And the Beckman equation is the well-known function. I borrow it from the transportation researcher, and it is often used to characterize the traffic equilibrium. And entropy functions takes probability as a variable, and it can characterize the travel patterns. And Beckman equation takes traffic count as a variable, and you can think the traffic count as a number of cars. And Beckman equation help us to consider congestion in the road network. So to summarize our objective function, the objective function is the linear summation of entropy functions and Beckman equation. We have total of 3 entropy functions, which correspond to each of the choice model for destination, mode choice, and the route choice. And by incorporating the Beckman equation, we can consider congestion in the route choice level. And by modeling all of this decision process in a single model, we can consider the impact of the congestion impact in the route choice on the mode choice and the destination choice. So we have this objective function, and then the remaining thing is to design our constraint. And we need constraint ensuring the travel pattern matches with the observations. So we have constraint related to conditional entropies and also momentum matchings. And since I mentioned that the objective function can be modeled as a convex function, the core technical details of our formulation is to design these constraint to not violate the convexity of the entire formulation. So our first theorem says the first stage model is a convex program. And after finding the conic representation of this convex program, we can utilize the off-the-shelf conic solver like Mosaic, SCS, and ECOS. And it gives us the tractability and scalability of the real-world scale network. So we tested our model in Sioux Falls, Anaheim, and Eastern Massachusetts. So as we increase the size of the network, our solution time increased, but we were able to calculate all of these, find the solution for all of this network within approximately 3 minutes. So we showed the scalability of the real-world scale network. And the first theorems give us the second theorem. By solving the KKT condition, we can prove that our optimal primer and dual solution satisfy the hierarchical logic model. Our primer solution characterizes the travel equilibrium, and our dual solution give us the parameter estimate. So you can think our dual problem is something similar to maximum likelihood estimate, but our problem is unique because of the constraint for observations. So as an extension of this research, we are in the process of validating this model using the real-world data. So we are collaborating with National University of Singapore, and we graph the network in Singapore, and we use cell phone location data, smart car data, taxi data, and household travel survey data. To conclude my talk, I would like to recall what are the challenges in complex and interconnected systems, especially in smart mobility system. So there are complicated human behavior, there are multiple stakeholders, and there are strategic interaction, and there are some inherent complexity within the network. And those components are interconnected to each other. So what I've been proposed is the foundation of how to integrate those two modeling paradigm on supply side and the demand side. And we saw the benefit of the integrated framework in 3 different transportation applications. So in the first project, we saw how the behavior-aware real-time operation for mobility on demand can increase the company's profitability. And in the second project, we saw how we can model seemingly intractable multi-agent game using the tractable convex programming. And in the last project, we saw how we can eliminate the manual calibration and automate the decision-making process. And my ultimate goal is to create the integrated and automate decision-making system. And to achieve this goal, I'm going to integrate supply and demand side as I did earlier. And I'm going to combine macro to micro scale. And I'm going to blend the design to operation problem. Lastly, I would like to thank to all of my collaborator and sponsor, and I'll be happy to take any question you may have.
Thanks so much, Youngseo, for the nice talk. Let's open the stage for questions. You can either type in the chat or put it or ask it directly. Maybe, okay, I'll start with the nice break. Of course, I'm biased because I've seen this talk a couple of times now, so I know many of the things.
Yeah.
But since you had to go quite quickly on the future steps, do you want to elaborate a bit more, maybe on a specific project or two? Do you have in mind?
Right. Yeah, that's a really good question. So so since I've already talked about some of the direct extension, I'll just throw some of the keywords. I think for the first few years, I want to focus more on the urban smart mobility, like the integration of connected and autonomous vehicle, and like I want to explore more on the multimodal transportation platform, like mobility as a service, and try to like collaborate with public transit agencies and private agencies and like working on some pilot projects. So that would be some like some research plan for the near future. But I'm also open to other domains like so I'm thinking of transferring the core technique, like connecting the demand and the supply side to other related fields. So whichever field having the aspect of network environment, and if they have some demand and supply side, I think we can transfer our core technique to other applications like supply chain management, maritime operation, and so on.
Nice, thanks. Any other question for Youngseo? See a silent audience today. Maybe okay. Since we worked on that together, you mentioned at some point you are now currently extending the work to multiple companies. It was the second second part.
Right.
What's the big challenge there? Do you
Oh,
want
big
to
challenge.
elaborate?
Oh, right. Yeah. That's a good question. So, the main challenge is, I think we can extend this research to two company situation, but if the number of companies becomes more than three, then we cannot find some analytical solution for the equilibrium. So what I'm thinking instead is to find the empirical equilibrium. So we can treat each company's decision making as one convex program, and I want to keep iterate through the solution so that we can find at least some empirical evidence of the equilibrium.
I see. So this is the common problem when extending this, but it's still very interesting. I would be interested in seeing if you can compute things efficiently, or if there are any other bottlenecks.
Right. Yeah.
All
And
right. It doesn't. Oh no, sorry. Go ahead.
No. Oh, no. I think another challenge is to validate this model actually. So because we are relying on some of the assumptions that travelers will maximize their utility and companies will only cares about their profit, but in the real world it might not be the truth. So validating our model using the real world data, it's one other challenges.
Yeah, that's always a big challenge. So I don't see any other questions. I think people will reach out and things will explode in the coming months because you will start a new job. Thanks so much again for the talk, and thanks everyone for joining, and good luck for the next steps.
Thank you for inviting me again.
All right, bye. Take care. Have a great week.
Bye.